Okay, so let's talk about some graphing when it comes to these exponential functions. And if you recall, whenever we were dealing with graphing, we were able to shift and translate graphs either by horizontal or vertical shifts by adding or subtracting appropriately to the inside of the function x for a horizontal shift or to the outside of the function for a vertical shift. We also had reflections where we could reflect by multiplying x by a -1 in order to shift horizontally, side to side, or vertical reflection where we shifted up and down with our graphs. We also had graphs where we could shrink or stretch by some constant, c. And so that constant times f of x gave us a stretch or a shrink appropriately. Well, let's just talk about some simple shifts right here. And let's say we're asked to explain how to use the graph of f of x equals 3/4 to the x to produce the graph of each of the following. So we've got this function here, j of x. And j of x is the kind of function where we take the base 3/4 to the x, and this time we're adding 2 to the outside of it. So we look at what's happening right here. And it looks like this is going to be a vertical shift in this particular case because our graph is having this addition of 2 to the outside of f of x, right? So in fact, j of x we could think of as being the kind of function that's taking whatever f of x is and shifting it up 2. So we would express that. Shift the graph upward by 2 points. So let's take a look at what that means right here for us. If we were to look at this particular function and compare it to the original one, what should that do? Well, of course, that's going to cause a graph whose shift is up by 2 points right here. So instead of passing through the point 0, 1, our graph should pass through the point 0, 3. And you can see some of the other points right here as well. Right here, this graph passed to the point 0 or 1, 3, 4. So now it's going to pass through 1, 3 and 3/4. Or instead of passing through the point -1, 4/3, it's going to pass through -1 and 4/3 plus 2. So what we're doing is we're just adding 2 to each of these values, and it's a shift up by 2. Well, how about this other one? What happens with it? Well, one thing that we can tell about this one is that we're adding 2 to the exponent right here. And since the function is based on the exponent, adding 2 actually changes the position as a shift to the left by 2 points. So this says shift the graph left by 2 points. So if we look at this graph, instead of passing through the point 0, 1 on the original function, here I'll do this one in green, instead of going through the point 0, 1 on the original function, our graph should now be passing through the point -2, 1. And a really good way to tell that is take the exponent. If we set the exponent x plus 2 equal to 0, so that we get a function 3/4 to the 0, we find that that happens at x equals -2 this time. And we can verify this by actually taking a look at our function here and graphing it. So if I look at my function and graph it, yep, sure enough, it looks as though this has been the graph of this original function shifted to the left by 2 points. So at -1, we can say that this graph passes through the point 3/4. Or at -3, it's going to go through 4/3. All the points that we initially had on our graph are shifted to the left by 2. Okay, so that's our graph. We'll get into some more stuff in the next video here. Well, before we get to the next video, let's try another one right here. Let's try this one. We've got the function, we want to use the function f of x equals 2 to the x to produce the graph of the following. some more shifts, right? So let's take a look at this. If the graph of f of x is the function 2 to the x, we want to compare what that is going to look like if we take negative of 2 to the x. And I want to be very careful to make sure I'm noting the notation right here. This negative is not being raised to the x power. Remember that we said that the base must be greater than 0, so what does this really mean? Well, even though the function doesn't have this particular notation attached to it, we would want to make sure that we understand that we're really talking about the negative of the function 2 to the x. And the reason is that that negative cannot apply to the base. So what is that going to do to it? Well, if we take a look at this function, a negative on the outside of the function means typically that we're going to take the original function and reflect it vertically. And that goes along with what we said before, because m of x right here is equal to the negative of the original function f of x. So that's a vertical reflection. And we can certainly compare that by looking at these two graphs. Here's my function. Come on now. Here's my function, y equals 2 to the x, and let's take a look at it in comparison to the negative of 2 to the x. Yeah, that shifts it all right. And I'm going to take this graph, I'm going to just change its position a little bit right here so we see the whole effect. There it is. Our function has been shifted upward, has been reflected about the horizontal axis. It's a vertical reflection. Okay, reflection, there we go. Looks a little bit more reflective-y. All right, how about this one? We've got y equals 2 to the x versus y equals 1/4 times 2 to the x. Well, in this case, this is actually a vertical shrink. Right? This is our vertical stretch, maybe, or shrink by a factor of 1/4. Pardon me, by a factor of 1/4. Well, what does that mean? Vertical stretch by a factor of 1/4 means that whenever we look at this function, any values where we would have had y equals 1 are going to be y equals 1/4, right? So in our original function, we might have had a graph passing through 0, 1. We should now see our graph passing through 0, 1/4. Where we had a graph that would have been at, let's see, if we're talking about 2 to the x, passing through 0 through 1, 2, right? We now are going to see 2 times 1/4, so it'll be passing through 1/2. The graph at x equals 2 would have normally passed through y equals 4, but now the graph should pass through the point y equals 1. And we can keep going to the left, right? Negative 1/2, 1/4 of that is 1/8, and so on. So what's going to happen right here is that if we compare the shapes of these two graphs, y equals 2 to the x and y equals 1/4 times 2 to the x, we see that what's happening right here is that the graph is stretching. It looks flatter as compared to the x-axis, and so it is 1/4. It's a vertical stretch. Oops, come on. The graph just doesn't want to play with me here today. Here, let me see if I can make this sit about where I had it before. There we go. Now let's take those pens. This is a vertical stretch. This is supposed to be quotation marks, stretch. So-called stretch because it looks as though the graph is being stretched out towards the x-axis a little bit more. There we go. Okay, so some easy shifts and translations to start us out with this basic graphing. More to come.